AP Chemistries, this is Mrs. Vanderlei bringing you another edition of Blankwalle. This is 15.7. This is all about bases. This is just like what we've been doing with your acids, where we talk about strong and weak acids, and the Kas, or in this case will be the Kbs. And so if you understood really how to set up the problems for your acids, you got this one down. So we start off with your strong bases, and there are pretty much these 6 strong bases, but there's a little problem with some of them. So your lithium, sodium, potassium hydroxides, if you remember your solubility rules, they are all 100% soluble. So I'll put that right here. And they will work fantastically all the time. Your strontium, your calcium, your barium, your magnesium, which is not on the list, the problem with that, they're not very soluble. Most hydroxides are not very soluble, so if you can't dissolve them, then they can't be a strong base. But those that do dissolve will be a strong base and will 100% dissociate. So it's not a problem of dissociation, it's really a problem of can they dissolve in water or not. So we have your group 1A metal hydroxides. Again, these are your sodium, potassium, and the lithium are all going to be very strong. Notice right here, sorry about that, we have the single arrow. Your group 2A, so that is your magnesium, your calcium, that they are less soluble, and if you can make them dissolve, they will dissolve. These are also used in antacids because they don't dissolve real well, but what does dissolve will then absorb any kind of additional acid in your stomach, and that's why they call them antacids. One thing to watch out for, when they do dissolve, they're going to produce 2 moles of hydroxide, so be aware of that. So let's calculate the pH of strong bases. So if you recall, the Kw for water was the hydroxide concentration times the hydronium concentration. Our Kw is 1 times 10 to the negative 14th. So if you know the hydroxide calculation or the molarity, you can calculate the hydrogen ion concentration, and you can calculate the pH. Or there's another way. To me, this is how I'm going to do it. I'm going to find the pOH, which is a negative log of hydroxide. Remember earlier I said you can take the P of anything. You can find the PA, the pKa, the PW, whatever you want to find the P of. It's just a negative log of anything. So if you know your hydroxide concentration, you can take the negative log of that and find pOH. And then what? You can find the pH by subtracting from 14. So pOH is 14 minus pH, or what else can we say? We can say that pH, oops, aren't you going to write? pH is equal to 14 minus pOH. So it's really whatever you're given and whatever you're solving for is how you're going to manipulate it. So let's go ahead and look at this next problem here. It says, what is the hydroxide concentration and the pH, not the pOH, the pH of each of the following? Well, the first thing to recognize is that KOH is a strong base and it has no problem dissolving. So we'll do the exact same thing as we did with a strong acid, one of those big 6s. So I set up an ice table, and if we start off with 0.225 molar, again, ice has molarity, not moles, molar solution here. I'll just kind of move these around a little bit. Then notice that we start off with no potassium, no hydroxide, but 100% of this will be converted into K plus and OH minus, and this is what's going to be really important. So now we need to define the pOH. This is what I do. And so it's negative log of 0.225, so the pOH is 0.645. And then again, we want to find what the pH value is, because that's just more common. We'll know acidic and basic based on the pH. So I put 14 minus 0.648, so the pH is 13.352. Why do I have all these sig figs? Remember, let's talk about this. There's really only 3 sig figs, the 0.352. The 13 really reflects your exponent, so that doesn't count in the sig figs, but the 0.352 does, because we start off with 3 sig figs over here. So in order to answer my question, the hydroxide concentration is 0.225 and the pH is 13.352. So what does it tell you? Man, is that a basic solution? It is well above 7. It is almost a 14, which is really the upper range of your pH, and it is extremely basic. Now, does that make sense to you? Well, hopefully, you have a fairly concentrated solution of a very strong base, so it should be very basic. So that pH does make sense. Now, what do you notice about the next one? We are talking about a group 2 hydroxide, so that's a problem as far as the dissolving. So it says if you can get it to dissolve. In the next chapter we're going to learn how to apply Le Chatelier and to force these hydroxides that don't commonly dissolve, we're going to make them dissolve. So if we can get them all to dissolve. So this is what I said. Assume you put a whole gob of strontium hydroxide solution, some of it dissolves to make this 0.0015 molar. Okay, so I'm going to put enough strontium hydroxide into the solution so enough of it will dissolve to make that kind of a concentration. So that's my assumption. All right, so what am I going to do next? Well, here is my strontium hydroxide. Now here is my arrow. Why is it a single arrow? Once again, because if it does dissolve, it is a strong base. Okay, so what dissolves will 100% dissociate. So I'll set up another ice table, and oops, I didn't quite get it to fit all in here. Hang on. There we go. So here we have 0.0015 of my initial, and I have 0. Now, what do you notice here? Why is it 0.0030 here? Well, do you remember what we said? For every 1 mole of strontium hydroxide, we get 2 moles of hydroxide. So if I have 0.0015 molar solution, I'll have twice the molar solution of hydroxide. So be very, very careful with that. So now we have, actually there should be an extra 0 at the end here, so make this 0.0030 for me. So now we know the hydroxide concentration. Now that what's left is find the pH. So here's my pOH is negative log of hydroxide. Here I got my sig figs right. There's a 0 at the end of the 3 here. And punch it into my calculator. And here is my pOH. But this is a really important concept here. Remember to answer the question. They're not asking you for what pOH is. They want to know what pH is. So now you got to go one more step and actually calculate your pH, and I got 11.48. And so what does that mean here? Excuse me. That the pH is above 7, so it's basic, but it's not as basic as the one above. And why is that? You started out with a much smaller concentration of the initial. Okay, that's your main fact right there, is that because this is a much smaller number, this is going to be a smaller number, so it's not going to be as basic, so my pH is going to be not as big as the other one was 13 point something. So it's still pretty basic, but not as much. Why? Because the initial concentration of the strontium hydroxide was not as big. Let's go on to the next page. All right, so now we're doing weak bases over here. Our setup is going to be identical. The ideas behind this are going to be identical to our weak acids. So if I put ammonia, which is not a hydroxide, a group 1 or group 2 hydroxide, if I put ammonia in water, will it 100% of the time act like a base? The answer is no, it won't. It will not accept H pluses all the time. So if I put it in, I'm going to have some NH3s left in solution. I'm going to have some hydroxides. Here's my molecular picture. So ammonia and other covalent bases, typically your organic bases, they're called amines. Notice how all these end in INE, amine. For your biology people, those amino acids have an amine group and a carboxylic acid group on both sides. They are the makeup of our proteins, if that makes any sense to you. So most of these are going to be your weak bases, and so here are your values of them. You also have a copy of page 721, which will also list more. So compounds with low values of Kb, so to the negative something. Like ammonia over here is 10 to the, or 1.8 times 10 to the negative fifth. So if I look over here, I go, what do you notice is not present in the above reaction? Well, first of all, I don't have any, I have a double arrow, not a single arrow, but what else is not present in the above reaction? Well, I don't have any H pluses. Why don't I have any H pluses? I had that last time with acids. Well, it's because I'm working with bases. You're going to have hydroxides and H pluses. So now what? Write the KB. All right, how do you write a KB? Products over reactants. But wait a minute, there's a typo right here. Ooh, fix this, fix this. Water is never aqueous, is it? Water is always a liquid, and that's going to make a difference. So if water is a liquid, do that for me. Change it. Here, I'll do it. Try to do it here. This is an L, right? It's a liquid. You do not put that into the KB expression. So let's go ahead. There's my KB. Why does water have to be included? When we had our acids, I left out the H2O. It was assumed to be there. I didn't need it. But here, I do need the H2O because I need to have a proton donor someplace, and that's going to be your water. Your water is your acid. So here is my KB expression. It should look kind of familiar. And calculate the hydroxide for the pH of a weak base. Use the ice table just like before. So for problem number 33, let's check this out. Notice ammonia is a weak base, and here is its KB value. Now, I'm also kind of getting very happy over here. You can say Frodig. Why? Because it's to the negative fifth. So what am I thinking with negative fifth? I bet I can use that 5% rule. Okay, so let's just go ahead and set this up. All right, so here's our equation, and oops, I guess my arrows didn't follow with me here. And again, same as equation before. So because it's a weak base, I will put in my ice table, and I start off with 0.1 molar, and I'm going to subtract the x and from this side and add x to the other side. So there's my expression. So here's my law of mass action. And then I'm going to plug in my values here. But wait a minute. Remember what I said? Oh, that 10 to the negative fifth. Ik ben zeer vrolijk. Look what I can do right here. I can cross that minus x out. Just the minus x. So now I am left with this. After I crossed it out, I need to scooch this down a little bit. And so x squared. And if you do your math, and I get 0.00133. What should you always do is go back and check. So your 5% rule, so 5% of my initial concentration of ammonia is 0.1, so 5% of that is 0.005, which is bigger than what my X value is, so I can keep going with the problem. So I find my pOH, I'm going to scroll down again, and my hydroxide concentration is now what my X was. So here it is, and so here's my pOH. But wait, am I done yet? Nope, I need to find the pH. So 14 minus my pOH, and now I have a pH of 11.124. Again, why do I have 3 digits following my decimal? Because of my sig figs. I have 3 sig figs up here. The numbers after my decimal are my sig figs. My 11 represents the exponent. So does this answer make sense? Hopefully it does. It is above 7. It is a base, and even though it's a weak base, it's still going to be, the pH is above 7. So it makes a lot of sense to me. Let's go on. All right, so problem number 34. Find the hydroxide and the pH of 0.33 molar methylamine. Is this a strong or a weak base? Well, hopefully you thought, oh, it's a weak base. How do I know it's a weak base? It's not a hydroxide. It's not a group 1 or group 2 hydroxide. So look on that chart on page 721 and you'll find the KB. What I'd like you to do is to pause this and work through the whole problem like you did before, and then come back and check your work. So how did we do? Well, let's find out. So here is my work right here, and I have the ice table set up. I looked at my KB value. That's going to be an iffy one. So I tried it, and see what happens when I crossed out this minus x right here to make my math a whole lot easier. And I got x is 0.012. And because this molarity is fairly high, the 5% rule actually still worked, even with the negative fourth. I would always check your 5% rule if you have something to the negative fourth. And so there is my pH. Okay? So problem number 35, go ahead and try this, and then we'll come back and you can check your work. So I went ahead and checked my KB values, and you can see them all listed, and so put them in order of the strongest to weakest by looking at their KB values.